Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element tantalum. I have a very small sample of the element right here, a little bit hard for you to see. I'm sorry about that, but let's take a look at it. I put it on my scanner for you to see. If you look a little bit closer, you can see that it's a bright, shiny, silvery metal. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Tantalum is the 73rd element in the periodic table. Its atomic number is 73 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Anders Gustav Ekberg examined two minerals, one from Finland, now called tantalite, and another from the famous rare earth source in the town of Jitterby, Sweden. That mineral is now called yttrotantalite. He's credited with finding a new element in both minerals in 1802. To this day, there is an Anders Ekberg Tantalum Prize awarded, as you can see, for excellence in tantalum research and development. Kind of a tantalum Nobel Prize. Anders Ekberg called the new element tantalum after the Greek mythological figure Tantalus. In a gruesome story, after stealing food from the gods and becoming immortal himself, Tantalus tested the Greek god's power of omniscience by killing his own son, dicing him up, cooking him, and serving the dish to the gods to see if they were as all-seeing as their reputation claimed. Of course, Tantalus was found out and punished by being placed in a pool of water, which, if he bent down to drink, would recede from him, and the beautiful fruit growing nearby would also avoid his grasp, denying him food. Of course, this was for all eternity, since Tantalus was now immortal. We get our word tantalize from Tantalus. Anders Ekberg wrote, "This metal I call tantalum, partly in allusion to its incapacity, when immersed in acid, to absorb any and be saturated." There was some confusion because the year earlier, the British mineralogist and chemist Charles Hatchett had discovered the element niobium, then called columbium. This element is directly above tantalum in the periodic table, and because of this there were family resemblances between the two elements. The qualities of niobium and tantalum were so close they were thought to be the same element. Niobe, whom niobium was eventually named for, was the daughter of Tantalus. Niobe didn't fare much better than her father. Here we see a 1772 painting by Jacques-Louis David showing Niobe attempting, unsuccessfully, to shield her children from Artemis and Apollo, after which her children lay unburied for 9 days while she abstained from food. The two elements remained confused even in 1846 when a German chemist, Heinrich Rose, argued that there were two elements in the tantalite sample, but he was not able to prove his hypothesis experimentally to the satisfaction of others. The matter of those two separate elements was finally put to rest in 1864 by Christian Wilhelm Blomstrad, Henri Etienne Sainte-Claire de Ville, and Louis J. Troost. This was a difficult task since niobium and tantalum are almost identical chemically and very difficult to separate from each other. In the same year, 1864, our old friend Jean-Charles Galissard de Marignac also proved there were two unique elements. He also produced the first metallic sample of tantalum, though it was probably adulterated with some niobium. It took almost 40 years until 1903 for a pure sample of tantalum to be refined by Werner von Bolton. He used his tantalum to form filaments for light bulbs, as we'll see in a bit. Today, tantalite is the main commercial source for tantalum, though there are other tantalum-bearing minerals such as euxenite and yttrotantalite, which we saw earlier. As of 2015, the main producers of tantalum were Mozambique, Australia, Brazil, and China. Tantalum production was pretty steady until the mid-1990s when it really took off and almost quadrupled. This is probably because of the electronics industry. Tantalum is part of a large group in the middle of the periodic table called the transition metals. This section of the periodic table is where we fill the d electron orbital of the respective atoms. Tantalum is a hard, ductile, shiny, blue-gray metal that's highly corrosion-resistant. If you build a very thin layer of oxide on the surface of tantalum metal by anodizing it, you can create many colors depending on how thick you make the oxide layer. The element tantalum is very uncommon in the universe, coming in as the 83rd most abundant element in the universe by mass, only 8 parts per 100 billion, right at the bottom of this chart. As far as we can tell, there is no tantalum in the Sun at all. It's the 77th most abundant element in meteorites, 2 parts per 100 million, also near the bottom of the chart. Surprisingly common compared to everywhere else. In the crust of the Earth, it's the 55th most common element at 1.7 parts per million, a little more common than our next element, tungsten, at 1.1 parts per million. Tantalum is the 69th most abundant element in the oceans, virtually non-existent and almost undetectable at 2 parts per trillion. And lastly, like most of the elements in the upper reaches of the periodic table, there's no tantalum in us. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here you see each element square with a tiny chart of its own, showing that element's growth over the age of the universe by various processes. Tantalum is here. I understand this looks complicated, but let's look at just tantalum a little closer. The horizontal axis of this square represents time from the Big Bang to now. The vertical axis shows the proportion of tantalum created by various processes. About 1/2 of the tantalum present today is believed to be produced by dying low-mass stars, the magenta area, and the other half is produced in supernovae, the yellow area. A very small portion, that green icing on top, is produced in neutron star mergers. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 73 protons for tantalum. But there can be different numbers of neutrons in the nucleus. All these different forms, called isotopes, are chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 36 known isotopes of tantalum, and of these 36, there's only one stable, non-radioactive isotope, tantalum-181. Tantalum is therefore a monoisotopic element. There are 23 of those, by the way. You would think that the only stable isotope would make up all of the naturally occurring tantalum in the universe, but you'd be mistaken. It only makes up 99.988% of naturally occurring tantalum. What? As we'll see in the next slide, there's also a long-lived radioactive isotope, tantalum-180, that makes up the rest, coming in at a minuscule 0.012%. By the way, the word isotope comes from the Greek, isos meaning same or equal, and topos meaning place, since all these various forms of tantalum occupy the same place in the periodic table. Of the radioactive isotopes of tantalum, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest tantalum half-life is an excited state of tantalum-180 with a half-life greater than 1.2 quadrillion years. That's almost 87,000 times the age of the universe. So we shouldn't be surprised to find a bit of this stuff still hanging around. Though technically not stable, it's called observationally stable. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide. I chose 1,024 atoms because it's a power of 2, and we're going to be doing a lot of dividing by 2. If you wait 1 half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait 1 more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's 1 remaining atom after 10 half-lives. If you waited 1 more half-life, your remaining atom would have a 50-50 chance of decaying in that time. As with most elements, the price of tantalum varies widely with purity and the quantity you buy. 99% pure tantalum goes for about $360 per kilogram. Tantalum has a fairly high density at 16.65 grams per cubic centimeter. As a reminder, water has a density of 1 gram per cubic centimeter. I've put up more densities for you here. You can see that tantalum is denser than lead at 11.34 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. When I do this talk with an actual audience, I have a set of blocks so you can feel density for yourself, but we'll have to wait to do this until we're back face to face. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, tantalum's density is 16.65 grams per cubic centimeter, the magenta circle. It's the 10th densest element. Unfortunately, I don't have a block of tantalum. Given its price, the block would cost over $1,000. If there are any tantalum suppliers out there willing to donate a 2¼ inch cube to the cause, please contact me. It's one of the few elements between tungsten and lead that won't kill me with radioactivity, toxicity, or a cost larger than the national debt. Being one of the refractory metals, which I'll discuss in a bit, tantalum has a high melting point at 3,017 degrees Celsius, or 5,463 degrees Fahrenheit. It has the 5th highest melting point of the elements. It boils at a blistering 5,458 degrees Celsius, or 9,856 degrees Fahrenheit, making it the 3rd highest boiling point of all the elements. That's a whopping 2,441 degrees above its melting point. Tantalum has the 10th largest liquid temperature range of all the elements. The high melting point makes tantalum a member of a class of metals called refractory metals. These metals are extraordinarily resistant to heat and wear. They all share some properties, including a melting point above 2,000 degrees Celsius and high hardness at room temperature. They're chemically inert and have a relatively high density. These qualities make them useful as tools to work metals at high temperatures, for wire filaments in incandescent bulbs, casting molds, and chemical reaction vessels in corrosive environments. Though not quite as tough as the classic refractory metals we just discussed, some of the transition metals surrounding our central group share some of the same qualities, but to a lesser extent. Note that technetium is not included in this group since it must be made artificially and is highly radioactive. If we compare the size of the tantalum atom to that of hydrogen, we'd see something like this. The tantalum atom is about 4 times the size of hydrogen. Here's its electron structure. By the way, a picometer is a trillionth of a meter. Atoms are impressively small. Looking at all the element atom sizes, here we see them sorted from largest, cesium at the top left, to smallest, helium on the bottom right. Tantalum has the 22nd largest sized atom of the elements. Tantalum is a medium hard element, coming in at 6.5 on Mohs scale of hardness, about the same as silicon. Here's a chart of element hardness from the hardest, boron on the left, to the softest, cesium on the right, obviously not including liquids or gases. Tantalum is the 8th hardest element between iridium and ruthenium. Tantalum has the 12th lowest rate of thermal expansion of all the elements, 6.3 parts per million per Celsius degree. This means if you had a 1 meter long bar of tantalum and you heated it by 1 degree Celsius, it would get longer by only 6.3 millionths of a meter, or about 1/10 the diameter of a human hair. That's a very low expansion rate. Here's the periodic table of the spectra. Tantalum has a very complicated set of emission lines across the spectrum that can uniquely identify it to scientists. No other element gives off this unique set of colors. Let's take a look at a few applications of tantalum. Many of these are for its refractory nature, but there are major electronic applications and a few medical applications as well. Remember Werner von Bolten, the guy with the great mustache? He's the guy who first purified tantalum. He produced tantalum wire he knew could be heated to very high temperatures without melting. He got a brilliant idea. Instead of using carbon filaments in light bulbs, why not substitute tantalum wire for the hot filament? Tantalum can be heated hotter than carbon without damage. Hotter filaments are much more efficient and give off more light. These lamps were manufactured between 1903 and 1913 when tantalum was replaced by our next element, tungsten. Again, because of tantalum's high melting point, you can use it as a vessel to melt other substances. This is a tantalum evaporation boat. You place the substance you want to evaporate in the small hollow in the boat and pass a high current through the tantalum, heating it up. The substance vaporizes and coats nearby surfaces, like a mirror being coated with vaporized aluminum. Tungsten and molybdenum are also used for this application. Tantalum is used when you're concerned with corrosion resistance. A capacitor stores electric charge. Capacitors are a part of virtually all pieces of electronics. Tantalum capacitors are smaller than many other forms of this device and hold more charge for a given size and weight. They are, however, more expensive than other types of capacitors. Without tantalum capacitors, our modern miniature electronics wouldn't be so miniature. On the left, you see a group of tantalum capacitors, and on the right, you see the tantalum electrodes inside those capacitors that make up the bulk of the device. These commemorative coins were minted by the Bank of Kazakhstan, the location of the Baikonur Cosmodrome, the Russian spaceport. The coins are bimetallic, with a silver outer ring and a tantalum center. They feature the Apollo-Soyuz mission and the International Space Station. Sticking with coins for a moment, these are privately minted fantasy coins, both from tantalum. The right-hand one minted by the Shire Post Mint in a test run made of just tantalum. Eventually they minted this in indium. It's supposedly a Tolkien elvish coin made of mithril. Wasn't it the dwarves, not the elves, that made things from mithril? Anyway, the left coin is from some other fantasy country. Aside from a tiny bit possibly absorbed from the environment, your body does not use tantalum, and it has no known biological functions. However, it does have uses in the body, just not technically biological. Thin tantalum wire can be woven into sutures that do not corrode and that, in medical terms, is, quote, well tolerated, unquote, by body tissues. This is a skull plate made from tantalum used to replace a missing piece of your head bone. Again, it's non-corrosive and well tolerated in the body. Tantalum is a viable material for prostheses in other parts of the body as well. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about tantalum. Smaller and lighter, your tiny capacitors, digital darlings. In the next program in this series, I'll examine one of the densest and highest melting elements, tungsten. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element tantalum.